Welcome to this detailed explanation of the plant disease detection using Deep Learning project, a complete end-to-end solution designed to classify plant leaf diseases using state-of-the-art image recognition. This project uses EfficientNet V0, a powerful pre-trained convolutional neural network, to detect plant conditions such as early blight, late blight, and healthy leaves. Let's explore how this system works and why it is an important innovation in modern agriculture. In agriculture, plant diseases drastically reduce crop productivity and quality, leading to significant economic losses and impacting global food security. Traditional manual inspection is slow, labor-intensive, and depends heavily on expert experience, often missing early-stage infections. By applying AI-powered image classification, farmers can identify diseases early, prevent crop loss, and make data-driven decisions. This project provides a scalable and low-cost solution that can be deployed in mobile apps, web dashboards, or in-field monitoring tools, making advanced diagnostics accessible. The project comes with a structured dataset divided into training, validation, and testing sets, crucial for robust model development. A CSV manifest called dataset.csv maps each image to its class label, ensuring organized data management. A synthetic demo dataset with 90 images is included for quick starts, but the system is fully compatible with larger datasets such as Plant Village from Kaggle, which contains over 54,000 images across 14 crop species. This makes it ideal for both academic learning and real-world agricultural use. To ensure high accuracy, all images are pre-processed by resizing them to 224 by 224 pixels, a standard input size for EfficientNet V0. This is followed by normalizing pixel values to a consistent range, preparing them for optimal model performance. Real-time data augmentation is also applied, including random flips, rotations, zooms, and contrast changes. These steps help the model generalize better and handle real-world field images, which may vary significantly in lighting, angle, and background conditions. The model uses EfficientNet V0, a top-performing convolutional neural network pre-trained on ImageNet, known for its efficiency and accuracy. The base layers are initially frozen, so only the classification head is trained, allowing for rapid adaptation to new data. Once the model stabilizes, the top convolutional layers are unfrozen for fine-tuning, unlocking deeper feature learning. This transfer learning strategy gives high accuracy even with small datasets, leveraging knowledge from vast existing image databases. The model is trained using categorical cross-entropy with the Atom Optimizer, a robust and widely used optimization algorithm. Callbacks like model checkpoint and reduce LR on plateau help automatically manage learning rate and save the best version of the model, preventing overfitting. Here you can see the training and validation accuracy improving gradually over epochs, indicating effective learning and generalization. The validation loss also steadily decreases, confirming the model's ability to perform well on unseen data. Evaluation metrics include accuracy, classification reports, and confusion matrices, providing a comprehensive view of model performance. These metrics are crucial for understanding how well the model performs across different disease classes. The confusion matrix, in particular, reveals how well the model distinguishes among early blight, late blight, and healthy leaves, highlighting any specific misclassifications. It's a powerful tool for diagnosing model strengths and weaknesses. On the synthetic dataset, the model achieves promising accuracy, and on larger datasets like Plant Village, the accuracy can exceed 95% to 98% with proper fine-tuning. This demonstrates its potential for highly reliable disease detection. This project includes everything needed for a full academic or professional submission: a detailed Jupyter notebook, complete dataset folders, comprehensive documentation, and a project report and a professional PowerPoint presentation. Additionally, it features a Flask-based web app for real-time image prediction, allowing users to upload images and receive instant diagnoses. The trained model is exported in TensorFlow's saved model format and can be converted to TF Lite for efficient mobile deployment. By working through this project, Learners gain hands-on experience in image preprocessing, CNNs, transfer learning, and data augmentation. They also master evaluation techniques and practical deployment strategies, essential skills for modern AI applications. It's perfect for final-year engineering students, researchers in agri-tech, and AI beginners seeking real-world computer vision experience. This project bridges theoretical knowledge with practical application, preparing individuals for impactful careers. In summary, this deep learning project demonstrates how AI can support sustainable agriculture by providing fast, accurate plant disease detection. You receive a complete, reproducible, and deployment-ready solution that bridges machine learning with real-world impact. Thank you for watching this overview of our plant disease detection using deep learning project. We hope this has provided valuable insights into the future of agri-tech.